This is a video for 7.4, Infinite Geometric Series. So we left off on 7.3 where we talked about geometric sequences and series. The series that we did there, that formula, where we had the Sn equals A1 and then big parentheses, all that fun stuff. Oops, that's R. That's an R. Dang it. Bloop, bloop, bloop. That's an R. That formula was for finite series, meaning we were adding up like a set number of numbers. So whatever n was, that's how many terms we were adding together. So today we're going to talk about infinite geometric series. And the way this works is we're trying to add things up that go on forever, which is kind of a weird concept to think about. But I wanted to start by looking at a couple examples. So if we had an arithmetic series where we were adding up numbers that had some sort of adding or subtracting pattern to it. So let's say we did like 1 plus 4 plus 7 plus 10 plus 13 plus dot dot dot. So this will go on forever because of the dot dot dots. This has an adding pattern of 3, so the common difference is 3. But if we're adding all of these numbers together, and if we're doing this for forever, the numbers that we're adding onto this will keep getting bigger and bigger and bigger. So technically, we can't keep adding forever because it'll just reach infinity. The numbers will just keep getting bigger. There's no like stopping point to this. So with this, we can't really do an infinite arithmetic series. That's why we don't have a formula for it, because it'll just end up being infinity. Or even if I did a geometric series like this. Let's say we're multiplying by 2 every time. So with this series, I have 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus dot dot dot. Even for this one, because I know we're talking about a geometric series here, but we're talking about specifically an infinite one. So if we do this forever, these numbers, again, keep getting bigger and bigger and bigger. So if this were to add up all together, we'd still get infinity. So for this one, since the pattern was multiplying by 2, our common ratio is r equals 2, which doesn't really work still because we can't do this infinitely. But let's say we had something like this, where geometric series, let's say r equals 1/2. So we're dividing by 2 every time. So let's say we started with 1/2 plus 1/4 plus 1/8. So here, all of our numbers are technically getting smaller because, these are fractions. So when the denominator is bigger, it's technically a smaller number. So if it's getting smaller every time, all of these numbers, they're not getting bigger, so we're not going to eventually add up to infinity. I want to show you an example of this, like tangible example. I'm going to switch over here to this desk. So what I've done is I've taken a full sheet of paper, and I just kept cutting my piece of paper in half into smaller and smaller pieces. So here's my full sheet. I cut it in half, so there's half. Here's a quarter of the sheet of paper, so plus 1/4, plus 1/8, plus 1/16, plus 1/32, and so on. So if I keep cutting my piece of paper into smaller and smaller pieces by half, if I were to keep cutting this little piece forever and ever and ever, it would still be like when I added all of these pieces together, should still equal 1 because I just took a full sheet of paper and just kept cutting them in half. So this is my demonstration of how a geometric series, an infinite geometric series, still adds up to just a number. So since these are the numbers that represent that piece of paper, all of this just equals 1. When you add them all together, because there was my half sheet of paper plus a quarter sheet of paper plus an eighth sheet of paper and so on. All of that really just adds up to a full sheet of paper, so 1. So when this happens, and this only ever happens when r is less than 1, because all of these numbers have to keep getting smaller and smaller and smaller in order for this to work. So we use the formula capital S, for an infinite series equals A1 over 1 minus R. So if we tried this out with our geometric series here, A1 for us would be 1/2, because that's our first term. R would be 1 minus 1/2, since we were dividing by 2 each time. We would end up with 1/2 over 1 minus 1/2 is just 1/2. So that equals 1, which makes sense, because that's a full sheet of paper right there. Okay, so the only rule for our infinite series formula is that R has to be less than 1 in order for this formula to work. If it's greater than 1, then we end up with something like this, where we keep adding bigger and bigger numbers, which would just add up to infinity, and that doesn't make sense. So this is our formula. Let me highlight this. And I want to do a few more examples. So let's say we have an infinite series. So I'm going to start with I equals 1 for our first term number, going all the way to infinity, of negative 3 over 7i. So first, how do we tell if this is geometric or arithmetic? We're looking at this formula right here. It's got an exponent to it, so that automatically matches the geometric AN formula. So I know that A1 is, there's technically a 1 here, so that's A1, that's R. Okay, so in order to use our formula, we said R has to be less than 1. I wanted to add something here. Technically, it has to be the absolute value of R has to be less than 1, because if we look at R here, we have a negative in front. So obviously less than 1, but we also want to make sure it's a fraction of some sort. So when we use our formula, A1 over 1 minus R, A1 for us is 1, R is negative 3 over 7. So this gives us technically 1 plus 3 over 7, which is 7 over 7 plus 3 over 7 is 10 over 7. Keep, change, flip. So this infinite series will add up to 7 over 10. Okay. Another cool thing we can do with this formula is actually to rewrite repeating decimals. So let's say we had the repeating decimal 0.9 repeating. This is kind of cool because this technically equals 1, and I will show you why. So I'm going to rewrite my repeating decimal as 0.9 plus 0.09 plus 0.009 plus 0.0009 forever. So if I kept writing out all of these decimals, when I add them all up, I should get 0.9999999 forever, right? So if we look at this series right here, this is technically a geometric series. Here, R equals 0.01, or if you want to think about it as, 0.1, or if you want to think about it as you're dividing by 10 each time. And this is going on forever. A1 is 0.9. So if I plug this in, I have 0.9 divided by 1 minus 0.1. 1 minus 0.1 is just 0.9. So that equals 1. Thus, proof that 0.9 repeating is actually equal to 1. Kind of cool. Let's do one where we have multiple numbers. So 0.24 repeating. This is the same as 0.24 plus 0.0024 plus 0.00024, because, we got to leave the space for all of the numbers to add together, and so on. So R in this case, you're actually dividing by 100 each time, or 0.01 is our common ratio. So in this case, our A1 is 0.24 divided by 1 minus 0.01. 1 minus 0.01 is just 0.99. So as a fraction, if I multiplied, because I got decimals on top of fractions right now, I'm going to move the decimal place twice for both of my numerator and denominator. So it's kind of like multiplying the top and the bottom by 100. This gives me 24 over 99, which we can then reduce to 8 over 33. So we know 0.24 repeating as a fraction is just 8 over 33. It's kind of cool. All right, that's the end of my notes for 7.4.